pleasure of introducing Dr. Rachel Ward. She's an associate professor in the Department of Mathematics of the Institute of Computational Engineering and Science at University of Texas, Austin. She spent the last year as a visiting research scientist at Facebook AI Research. And prior to joining Texas, lots of accolades, 2 years as an NSF Mathematical Sciences postdoc fellow at Courant. She received her PhD in Applied and Computational Mathematics in 2009 from Princeton, where she was an NSF Graduate Research Fellow. Her interests are broad and diverse. We'll hear about one of them today. She's on the editorial board of a number of journals that reflect those interests, like Applied Harmonic and Computational Analysis, Information and Inference, Mathematical and Statistical and Learning, SIAM Multiscale, Modeling and Simulation, and SIAM's new Journal on Mathematics of Data Science. She was with her colleague, Dina Needle, awarded the 2016 IMA Prize in Mathematics and its applications for her contributions to the mathematics of machine learning and signal processing. Today, she's going to talk about stochastic gradient descent in theory and practice, so please help me in welcoming Rachel.
Thank you, Stefan, and thank you to the organizers for this invitation. Thank you to the audience for coming. I know there are other interesting things going on in the news, so thanks for coming to listen to me for a few minutes. So I want to talk about stochastic gradient descent. In my talk, we'll sort of follow a story of how I got into this area of research. I'm coming from a background in mathematical signal processing, and I sort of got into studying stochastic gradient descent from compressive sensing. And from there, proved some theory that I thought was very theoretical, maybe not so much practical use, but then it turned out to be more related to neural network optimization than I realized, and so Facebook AI Research asked me to come work for them for a bit. And now I know more about the practice of stochastic gradient descent, and some ways that the practice and the theory are surprisingly similar, and some ways in which they're different, in which case we can learn about the practice and let it help us guide new theory. So I'm in the math department at the University of Texas. I'm also associated with the Odin Institute for Computational Engineering and Sciences, formerly the Institute for Computational Engineering and Sciences, recently renamed, dedicated to Tinsley Odin, the founder. So if you hadn't heard that already, I'm happy to tell you that news. And so let's get started. So this talk isn't about neural networks, but stochastic gradient descent is sort of the optimization algorithm behind the scenes for powerful and versatile neural network methods that are being used more and more. So I'm going to motivate stochastic gradient descent with some neural network motivation. So neural networks, from my perspective as a mathematician, they're just functions of a particular parameterized form. That the parameterized form is modeled after the way human brains learn connections and classifications in the real world. And in the overparameterized setting, the neural network function will interpolate or approximate a given set of training examples, which in a very simple case could be examples of pictures of cats versus dogs, which are labeled. And the neural network function is just a function which correctly interpolates the training data and is such a function that hopefully will work well when you feed it examples of cats and dog pictures that you haven't labeled yet. And it can also correctly classify most of them. Why are these particular types of functions so powerful and versatile? Well, it's been known for a long time that these classes of functions have very strong approximation power. Universal approximators can approximate very rich classes of functions. And they have a simple form, which makes working with them easy in some sense. They've exploded in popularity recently because modern computer hardware can now handle very, very large dimensional problems. And simple optimization methods like stochastic gradient descent are key for learning good and interpolating neural network functions very quickly. So where do we stand regarding the theory versus the practice here? Just a little more details on the sort of neural network optimization setup. In the supervised setting, which is what we're talking about here, given a set of labeled training examples where the X's could be, say, images, and the Y's could be labels associated to those images, just minimize a simple quadratic loss function, for example, over a vector of weights, which parameterizes the family of neural network functions that we're fitting the labeled data to. A typical neural network function these days will look like a composition of many nonlinear operations composed of multiplying the training data X with matrices of weights, compositions of matrix multiplication, and hard thresholding. We call these sigmas activation functions. A popular one is the ReLU activation function, which, or if you want to make the neural network function smooth, just a smooth approximation of this ReLU function. These days, the depth that people can work with, the number of such compositions of these kinds of nonlinearities is growing. The depth D these days can be up to 100. All of the dimensions in these types of optimization problems these days are very large. The dimension of the training data is on the order of millions. The parameter space, the number of parameters that we're trying to optimize over, is even larger, if possible. And so when we're talking about problems in these dimensions, we have to use very simple, almost embarrassingly simple optimization methods to try to, say, minimize a loss function of this form. So optimization methods used are first order, meaning they only look at gradient evaluations of the loss function, and they're iterative. So think of gradient descent. Actually, gradient descent is too expensive, which is what we're going to get to. But I just want to have a quick remark that computing gradients of these seemingly complicated functions we're trying to minimize are actually not too difficult. It's not too difficult to compute a gradient using the chain rule for these types of functions. That's a key ingredient in the backpropagation component of neural network optimization, which is another reason for the popularity of stochastic gradient descent. So I lied. Even computing a full gradient doesn't pass the efficiency versus is not as efficient as instead, at each iteration of the iterative algorithm, instead of computing a full gradient of the loss function which can be expressed as an average of little n component functions, each component function is for a different training example. Choose at each iteration just a single component function or a little batch of component functions, and just go in the direction of the negative gradient of that one component function as a surrogate for the gradient descent direction. Stochastic gradient descent is just gradient descent, except at each iteration, instead of moving in the direction of the gradient of the full loss function, we just move in the direction, of the negative gradient of a component of the loss function. And importantly, we pick a component index at random so that this random gradient direction we move in is an unbiased estimate of the full gradient. Okay, so if we pick a component direction at random and go in the direction of that, the negative of the gradient of that component function, then we have an unbiased estimate of the gradient. But if you look at some sort of iteration of stochastic gradient descent, It's definitely a stochastic algorithm, and it doesn't just go straight towards a good minimizer. It bounces around into a neighborhood that's somewhat close to a minimizer and stays in that neighborhood. Stochastic gradient descent has been around for a really long time, first proposed by Robbins and Monroe in a setting very different from neural networks. They proposed it as a stochastic approximation algorithm for finding roots of functions, which can be written as the expectation of component functions. So stochastic gradient descent as an algorithm lives in a world beyond neural networks, but it's just very popular recently due to the popularity of neural networks. Okay, so there have been lots of theory about, say, the convergence of stochastic gradient descent in expectation with high probability for different classes of functions since the 50s. This is a talk based on my background and my experience, so it's biased towards what I know best. So I will just say that let's consider for this talk just the assumptions on the types of loss functions that give rise to the strongest theoretical convergence guarantees for stochastic gradient descent. So the strongest theoretical convergence guarantees assume quite a bit about the type of loss function we're minimizing. It might seem very strong, but later on you'll see that it's not too far from, say, the situation for over-parametrized neural networks. So we assume that each of the component functions is convex. The loss function, which is the average of the component functions, is strongly convex with parameter mu. So you can think of the loss function as being lower bounded by some quadratic uniformly everywhere. That's what mu strongly convex means. Each component function is smooth, L smooth, so basically its curvature is bounded by a number L globally. And this last point is not necessary, but it will give rise to the simplest theorems. So we're going to assume for now that all the component functions share a minimizer. There exists some set of weights, W star, in the intersection of the convex sets of minimizers of each of the component functions separately. Okay, so each component function is convex, so it has a convex set of minimizers. But this isn't trivial because we're not assuming each component function is strongly convex. So these convex sets aren't just points. But their intersection is non-empty. So in this setting, we have a well-defined notion of a condition number for this optimization problem. The condition number, a reasonable condition number, kappa, is the Lipschitz constant L over the strong convexity parameter mu. Okay? And we can state a very simple to state theorem describing the convergence rate of stochastic gradient descent to such a special minimizing point W star in terms of the condition number. So in this setting, the convergence of stochastic gradient descent iterates in expectation, because it's a random algorithm, but in expectation, the iterates will converge to such a minimizer W star at a linear rate, meaning we'll be within a neighborhood of epsilon after roughly log 1 over epsilon iterations, and the constant in the rate is just given by the condition number of the problem. So in the best case, L over mu is 1. Okay, so this is very analogous to the convergence rate of gradient descent, full gradient descent in the same setting, except that we're using a weaker notion of a condition number here than the condition number for full gradient descent. But in any case, there's this nice analogy saying that we don't lose much by going from gradient descent to stochastic gradient descent. Okay, this theorem is not so difficult to prove, but you could probably work it out during later talks or something if you have some time. Now, an even more special case is the case where we're trying to solve an overdetermined, consistent linear system. So within the previous framework, which seemed already quite strong in terms of the assumptions, a very important special case is where the loss function is just the quadratic loss for AW minus B, where we're trying to solve for a W star with the information that there exists a W star such that A W star equals B. We assume that A is overdetermined, meaning that there are more, A is a tall, thin matrix. In this case, the convex sets representing the sets of minimizers for each of the component functions are actually affine subspaces. And so stochastic gradient descent is equivalent in this case to an iterative projection onto convex sets algorithm. We're starting from an initial guess, W naught. What stochastic gradient descent does is it just iteratively projects onto the affine space corresponding to the set of minimizers for one row or one batch of rows for A, and then alternately projects onto another affine space corresponding to which row, I guess the random selection of the rows. Now, projection onto convex sets is a very old algorithm, not with random selection of the convex sets, but with cyclic selection. In particular, von Neumann in some 1933 lecture notes wrote out a proof of linear convergence for the projection onto convex sets algorithm in the case when you just have two convex sets and they're just affine. So this is in the setting of least squares. If you see this picture here, you can see that the order in which we select the rows is important for determining the convergence rate. If you can see there, we have a number of affine sets in a certain order, and if we just select the rows of A in a cyclic, not random order, corresponding to the ordering of those subspaces, then the iterative projection will converge quite slowly to the global minimizer W star. So that's sort of a motivation for why random selection rather than worst case cyclic selection could give a faster convergence rate. We'll get to that more in the next slide. But first I want to say, because we're going to come back to this, that for linear systems in particular, they're very special. We can say special things about stochastic gradient descent. For example, in case there isn't a W star satisfying A W star equals B, if there's noise on the measurements, then stochastic gradient descent will converge to the least squares solution. So the solution W that minimizes A W minus B. Moreover, in the underdetermined setting, where we have a short fat matrix, stochastic gradient, and there are infinitely many possible solutions to the underdetermined system, stochastic gradient descent will converge to a very special one. It will always converge to the solution of minimal L2 norm among the infinitely many solutions. And that can be observed simply by the fact that stochastic gradient descent always selects a direction in the range space of the matrix, and the only solution to the linear system in the range space is the least norm solution. So what that says is that stochastic gradient descent and gradient descent as algorithms implicitly regularize. The optimization algorithm itself, when there are infinitely many possible solutions to that minimized optimization problem, the algorithm implicitly goes to a special a special solution. And this is completely understood in the setting where the optimization loss function is just least squares. Okay. But we're going to come back to this. So just a brief aside back on the convergence rate and how the order or the selection scheme we have for selecting rows from the matrix will determine the convergence rate. The condition number, L over mu, that I talked about before for stochastic gradient descent. In the case of linear systems, we see that this condition number corresponds to n times the max squared L2 norm of any of the rows of the matrix times the operator norm of the pseudo-inverse of A transpose A. Okay, this is a sort of strange condition number. And in fact, you can get faster convergence if you don't select rows uniformly at random, but rather do some importance sampling, where you select rows at random, but proportionally to the square of the L2 norm of the row of A. So rows with larger L2 norm are selected with higher probability. In that case, Stromer and Verschinen showed that the convergence rate of stochastic gradient descent for linear systems can be improved to have constant, which is the Frobenius norm of the matrix squared times the inverse. So this is closer to the true condition number. Note that if we were doing full gradient descent instead of stochastic, the rate of convergence would be the usual condition number, the operator norm of the matrix squared times the pseudo-inverse. So by choosing the selection scheme for the rows according to some importance sampling, we can get faster convergence for stochastic gradient descent, not as fast as full gradient descent, but of course, we can't expect that because gradient descent takes in all the rows at once, where stochastic gradient descent just takes in one. And then what we did in 2013 or so was generalize the stochastic Verschinen result to a more general theorem about speeding up the convergence rate of stochastic gradient descent in the setting of convex smooth functions I mentioned by doing importance sampling, where you don't choose component functions at random uniformly, but at random weighted according to the component Lipschitz constants. Okay. So at that point, when we did this work, I thought that this setting of assuming that your loss function was strongly convex, that the component functions were smooth, that the component functions were convex, that the component functions share a minimizer, was just very strong and had nothing to do with optimizing neural networks. But in fact, they have a lot to do with the optimization problems in neural networks. So now we're going to go from linear systems back to the optimization problems in neural networks. Recall a general form of the type of optimization problem. We just have a quadratic loss where we want to fit a neural network function parameterized by a vector or a matrix of weights. And so we just want to minimize the set of weights W. This is a highly non-convex, highly nonlinear optimization problem due to the composition of the sigmoid, of the several nonlinear sigmoid functions. So, okay, so what does stochastic gradient descent do? This is a very nonlinear function. It's not going to, say, find a global minimizer of this function, right? But if we look at some typical plots illustrating the convergence of stochastic gradient descent for some of these problems, so this is a plot. Don't worry about the labels. The important thing is that we're plotting the number of epochs over the data, the number of times we go through all of our training data on the x-axis, and the y-axis is just the value of the loss function, f of w, as wt, as t increases. Okay, so it's just showing the value of the loss function, aka the training error. And we see this looks like several different parameter settings of the neural network, that stochastic gradient descent, will find a W star that gives a value of 0 for the loss function. Okay, well, if it finds a W star where f of W star is 0, that's definitely a global minimizer because f is a non-negative function. So stochastic gradient descent will find global minimizers to these seemingly highly non-convex optimization problems. This is something that has only been observed recently in the over-parametrized setting, where our computing power is so great that we can optimize over parameter vectors or matrices W, which are so large that they're larger than the dimension of the input data. In other words, we're lifting our search space, our optimization domain, in this dimension that's so high. We know that in general, lifting complicated optimization problems to higher dimension will simplify the problem, often make the problem convex or linear. And here we have the computing power to lift the dimension so high that we're essentially in the setting where there are infinitely many possible values of W star that exactly interpolate the training data. That means over-parametrized. So that's the reason why there exists a set of weights W where the loss function is 0. And somehow stochastic gradient descent is converging to one of these points. And I just want to say that this really contradicts the thought for many decades, or the thinking, which is that neural network optimization is NP hard or very hard. Well, it's not that hard in the over-parametrized setting, apparently. So that's one surprise. But now if we plot not only the training error, as I did before, but next to the training error, testing error. The testing error is where we plot the value of the loss function now when we input training examples to it that it hadn't seen before. So we optimize it using a set of training examples. And now we look at the testing error, or how the loss function fits data that it has not seen before. And we see that stochastic gradient descent, as we train longer and longer, we're not overfitting. As we train longer and longer and find a point that gives 0 training error, the testing error doesn't go up, which is also against the conventional wisdom that if you want to fit your training data perfectly, you're going to overfit and do worse on the holdout set. But this is saying, no, we're not doing worse. We're fitting the training data exactly, and we still have pretty low error on the holdout set. So what this is saying is that stochastic gradient descent tends to converge to global minimizers of over-parametrized neural network functions, and not any global minimizer, but it somehow converges to among the infinitely many possible, set of weights that result in 0 training error. It converges to one that has low generalization error. So a picture of this could be we just have this 2 sets of data, the open circles and the dark circles, and any neural network, which is a function that separates the black from the white circles, results in 0 training error, and stochastic gradient descent will converge to the red separating line, which is the solution which maximizes the margin, maximizes the distance between to any white circle or any black circle. So this is a sort of analogy to how stochastic gradient descent in the underdetermined linear systems case converges to the special solution of smallest L2 norm. That tendency is carrying over to neural networks in some sense. We're seeing implicit regularization. Okay, So in the past 5 or 10 years, people have been deriving some theoretical results to explain some of this surprising behavior. And so these results in a nutshell are saying that for overparameterized neural networks, where we have the computing power to optimize over a number of parameters that's larger than the size of the input data, that stochastic gradient descent acts surprisingly similar to how it behaves for just finding solutions to linear systems. So for sufficiently overparameterized neural networks, some recent work has shown that stochastic gradient descent will provably converge to global minimizers at a linear convergence rate. The idea is that the optimization problem, although highly non-convex, locally is strongly convex. Locally, and so if you start with a random initialization for your weight, there will be a global minimizer in a neighborhood of your random initialization where the function is strongly convex. So this is just the general philosophy of you can lift a hard optimization problem to a high enough dimensional space, it becomes a much nicer optimization problem. Another line of work has shown that at least for shallow neural networks, we don't know about deep neural networks, but for shallow neural networks where you just have compositions of 1 or 2 nonlinearities, gradient descent is shown to provably converge to the minimum norm solution. So the implicit regularization of the optimization algorithm is confirmed. And note that this is a property of the optimization algorithm, gradient descent, this implicit regularization. Okay. So in the last 5 minutes or so, I just want to mention, I hope I haven't given you the impression that we think neural networks are easy now, or that all the problems are solved. I just wanted to convey that in certain cases, say if we have the power to make our systems overparameterized, understanding neural networks is easier in that setting. But still, the way that people use stochastic gradient descent in practice is not completely honest, in the sense that the plots that I've shown you, the general plots that are published in papers on the convergence rate or the speed of the training speed for stochastic gradient descent are the result of lots of hyperparameter tuning, lots of plotting, maybe hundreds or thousands of such plots using different parameters, hyperparameters in the stochastic gradient descent algorithm, and just choosing those hyperparameters that give the best convergence to publish. Now, this is far from the philosophy that, say, Professor Jorge Nos et al. Put forth in 2012, saying that in machine learning, these very large problems, we're not going to be able to use optimization methods as ideal as Newton's method, but at least we should use algorithms that tend to have the right length, i.e. the step size of 1 will be working most of the time. And this is very far from the situation in practice and theory now, where there's a lot of guessing going on. So I here's a screenshot of an earlier slide from my talk. I don't know if you can see this, but when I was talking about stochastic gradient theory, the nice convergence rate I was telling you about crucially depended on the step size alpha being a certain value, 1 over 2L, where L was the smoothness constant associated to the component functions. Okay, so if the step size is chosen at that particular value, then we have this nice convergence. Now, in actuality, stochastic gradient descent is very sensitive to the choice of step size. If the step size if the Lipschitz constant, the smoothness constant is not known a priori, which it isn't, and the step size is chosen that's just a factor of 2 bigger than this critical value, stochastic gradient descent will diverge. It just is it's not robust at all. If the step size is chosen to be too small, it will converge, but slowly. We have a similar problem in gradient descent, just full gradient descent, with constant step size. It's notoriously sensitive to the choice of constant step size. In gradient descent, though, we can do line search methods to approximately find the step size corresponding to the method of steepest descent. And line search methods for gradient descent work very well, and so this isn't really a problem in gradient descent. But line searches don't work well for stochastic gradient descent. You don't want to overfit to a direction which isn't actually the gradient direction. It might not even be a descent direction. You don't want to spend too much time trying to figure out exactly how far in that direction you should go when it's not the correct direction in the first place. So choosing the step size in stochastic gradient descent is a very open problem. In practice, people spend, for neural network optimization, people will spend days or weeks and millions of dollars in GPU time to run stochastic gradient descent on a given set of training data using various choices of step sizes or step size, piecewise, constant decaying step size schedules of the form. Fix a certain step size alpha naught for a certain number of epochs through the data, then decrease it by a factor of 10, say, and then decrease it by a factor of 10. Different factors, different alphas, plot all of the convergence rates and pick the best one. Okay. This is something, which if we want to implement stochastic gradient descent and do machine learning in a truly online or one-pass fashion, we clearly can't keep doing this. Now, in the past recent years, there have been several tricks or heuristics developed to add on to stochastic gradient descent to make it more robust to hyperparameters such as a step size. One of the original tricks, one of the simplest ones, is called addigrad. And I just want to show you what stochastic gradient descent with the addigrad type of adaptive learning rate or step size is. In addigrad, we still have a step size parameter alpha, but at each iteration of stochastic gradient descent, we divide alpha by the root mean square of the norms of all of the gradients of component functions that we've observed so far along the way. That's what the denominator is. So what this does, addigrad, is it forces a step size decrease. So if you start with an initial guess of alpha that's too large, you're not going to diverge anymore. It's going to force the step size to decrease because if the gradient norms are big, then this will push the alpha down. And it's been observed empirically that it decreases to a critical correct value of the step size and then stabilizes automatically. And that wasn't understood until recently. It was sort of a heuristic until recently. We did some theorems on this. Okay, so we tried to make the following. We made the following intuition rigorous. In that if the component functions are smooth, then by looking at the descent lemma, just for what's it called? For smooth functions, the Taylor expansion, you can work out that basically the norms of the gradients will go to 0 fast enough that if you start at a step size that's too big in expectation, it will decrease to a value that's not too much smaller than the critical value, which is 1 over the Lipschitz constant. That's in the case of smooth functions. Moreover, if your component functions don't all share a minimizer and there's some noise, which is especially the situation for generative adversarial networks, the unsupervised learning case, then this adaptive step size update will converge on a decreasing step size rate which corresponds to 1 over square root t, which is an optimal rate for the step size in the setting where you have noise in a smooth loss function. So just sort of that this explaining why this particular update is good. And an informal version of a theorem that we proved was that for a certain class of optimization problems, which are smooth, This stochastic gradient descent with this addigrad adaptive step size update will always converge, whereas stochastic gradient descent with fixed step size will diverge if it's too big by just a factor of 2. Addigrad will always converge, and in a wide range of choices of initial parameter B naught and choice of alpha up there. It will converge just as fast as stochastic gradient descent converges if you pick the step size carefully with knowledge of the Lipschitz constant and the level of noise, which of course in practice you don't know. So in other words, we showed that a theorem that says that for a certain general class of functions, addigrad is a type of universal algorithm. It converges at the same rate as stochastic gradient descent without needing to know prior knowledge about Lipschitz constant or noise. And this is just a plot showing for an overparametrized neural network how addigrad in red will converge to a W star that is a global minimizer of the loss function starting from sort of a wide choice of initial guess of step size, whereas stochastic gradient descent with fixed step size will converge very well for some step size choices and then just fall off and diverge suddenly if you choose a step size too big. So this is a sort of plots of robustness. So we motivated the use of stochastic gradient descent, why it's so popular for optimizing neural networks. In the past several years, really, there's been a lot of work in understanding why stochastic gradient descent works so well, especially in the overparameterized context. Neural networks behave very similarly to systems of underdetermined linear systems, which are well understood theoretically. Still, the way stochastic gradient descent is used in the practice in modern machine learning is far from being online. There's a lot of time-consuming and expensive hyperparameter tuning that goes on before the algorithm is deployed in the world. So a lot of recent work is also on understanding some of these new tricks for making stochastic gradient descent more robust. I talked about addigrad, but in practice, there are even more powerful adaptive gradient methods, such as batch normalization, that we don't understand. So there's a lot of work there. And just some open questions are generative adversarial networks, neural networks which are not supervised, but aren't given training data, but are unsupervised, are even more powerful in practice and even more sensitive to hyperparameters, such as this choice of step size. So this sort of finding good, robust algorithms is even more important in that context. And thank you. Thank you for listening.
Thank you, Rachel, for that great talk. If you have a question, if you can please step up to the microphone. We'll start right here.
Do you think there's any hope for designing a more conventional regularization that does the same thing as SGD does implicitly?
What do you mean by conventional regularization?
Like create a regularization function that you would add on to the objective function, and then it would do the same thing as SGD is doing, but you could optimize it with more conventional techniques.
So those sorts of regularizations like weight decay was used for a while for that purpose, which is a more like L2 type of conventional regularization. Isn't competitive at all with just plain stochastic gradient descent with add-ons like batch normalization.
I was just thinking the existing regularization isn't very good. SGD does regularization very well. Maybe find out what it's doing and then directly put that into the objective.
I understand.
You think
Sure.
there's hope for that? Is there hope for that?
There is hope. But at the same time, stochastic gradient descent is kind of mimicking what we do as humans in the sense that it's iterative, and we start out not really knowing connections, and some connections are reinforced and some are damped down, and we sort of wobble randomly towards a good set of weights.
Thanks.
One last question, Tobin.
Hi. In terms of going from the overdetermined to the underdetermined case, Is there anything where we can say something about the size of the discrepancy enters into any kind of convergence rates or anything like that?
What do you mean by discrepancy?
So if it's underdetermined and we may have the point of smallest L2 norm that the model can achieve close to the true data that we're trying to match. So if that discrepancy is small, we might expect that we could do something similar to overdetermined.
That's a good idea. That's reasonable. It's conjectured that a critical over-parameterization ratio is just like n log n, if n is the number of training samples, and right now the theory requires, say, like polynomial in n over parameterization ratio. So I think even understanding that sort of critical threshold would be a first start, and then to understand what you say.
Thank you.
Great. Let's thank Rachel again.